So where we left off last time is looking at how air flows around balls, with leading into finally in 10 minutes, 20 minutes, we'll get into the real aerodynamic systems like airplanes. Something that really uses air constructively. With balls, it's about air resistance primarily, although, well, we'll see. There's more opportunity to make things happen with balls than first appears. Anyhow, to sort of rehash the story, when air flows past a ball, so we'll take the ball's perspective, it encounters the ball, it spreads out on the ball's front surface, bending away from the surface. So there's a high pressure region in the front of the ball, bends toward the ball on the sides, so there's a low pressure region on the sides of the ball. And then what happens after the ball, at the back of the ball, depends enormously on how fast the air is flowing past the ball and also how big the ball is. Basically, it's the battle between viscosity and inertia there on the back of the ball, ultimately producing turbulence if you're not careful. And for all practical purposes, there's always turbulence behind real balls and real sports. So if the ball goes extraordinarily slowly or is just minuscule, basically dust particles moving through the air, then the flow on the back of the ball manages to remain laminar. It retains its streamlines all the way to the back of the ball and leaves the ball behind. And as it does, it bends away from the ball, and the pressure at the back of the ball oddly rises. So a ball that has no turbulence would have a high pressure region on the back that exactly balances the high pressure region on the front. Alas, that never happens in a real ball sports. You always end up with turbulence behind the ball. And so the high pressure at the front of the ball is never balanced by low pressure, by high pressure at the back of the ball. And so there's always a backward push on the ball, which is given the name pressure drag. It pushes the ball downwind, and it gets worse as you go faster. And I tried to explain last time why it goes as the square of your speed, so that if you double the speed of the ball through the air, it gets 4 times as much pressure drag. Any thoughts or questions about those, just the drag issues? Okay. The one peculiar thing that happens with that turbulent wake that forms behind the ball, normally, or in most situations, it's pretty much the size of the ball in cross-section. So it's a column heading off behind the ball that's about as big around as the ball itself. Depends a little bit on the shape of the ball, and this is certainly a consequence for the modern era of trying to conserve ordered energy. Thermal energy is present in abundance. We don't need to conserve that. It's ordered energy that we need to conserve and try to use carefully. In any case, different vehicles and objects moving through the air leave different sized turbulent wakes behind them. And the bigger that wake is, the worse the air resistance. So designing cars, planes, trains, all of them, so that they leave as small turbulent wakes behind them as possible is certainly part of the modern intention of manufacturing and design. There is a peculiar thing that happens when the air goes extremely fast over the surface of a ball. That turbulent wake at the back of the ball actually gets smaller, which is strange and counterintuitive. It happens because of turbulence that shows up in the boundary layer of air that actually interacts with the surface. So the layers of air that are touching the surface of the ball or almost touching the surface of the ball and are aware of that surface, if those layers remain laminar, if they flow smoothly to the back, oddly enough, that ultimately triggers a big turbulent wake. But if those boundary layers tumble a little bit and replace one another, play exchange with one another, they can work together to get to the back of the ball better. And they still trigger a turbulent wake eventually, but it's a smaller turbulent wake. So at high speeds, balls going through air, or high-speed air going past balls, it actually leaves an oddly small turbulent wake behind the ball. And that affects things like a batted ball in baseball goes fast enough to have that happen. A thrown ball doesn't go fast enough to have that happen. okay? It's just one of those oddities of aerodynamics that you have this effect occur. It's the effect that is deliberately caused by dimples on a golf ball. That turbulent weight, the turbulent boundary layer is there at the surface of the golf ball, and the golf ball consequently leaves a remarkably small wake behind it, and it flies much better than it would if it were smooth. All right. So on to what? The next thing to talk about. Oh, actually, even before this, I'll talk about. I want to talk about both curveballs and knuckleballs if I can manage it. Curveball, both would show up in every sport, but I tend to focus on baseballs and forget to carry them over to the other sports, but they're all there. If a ball, up until now, I've had the ball surface essentially not moving. We're with the ball, and the air is flowing past it, and the ball just sits there. But if the ball is spinning, it interacts with the layer of air nearest its surface, the famous boundary layer, and that boundary layer knows the ball is spinning. And that changes the airflow around the ball. It makes it asymmetric. It depends on how the ball is spinning. If the air continues to come along from your left, heading rightward, the airflow over the ball, if the ball is spinning like this, the airflow over the ball is going with the ball, and the airflow under the ball is going against the ball. Is that reasonable? The one strange possibility is if the ball is spinning like this, the air is swirled universally around. There's no asymmetry to it. But if it's most other spins, maybe all other spins, have some weird symmetry to them or asymmetry to them and do interesting things. So I'm going to talk about the effects that occur as the air flows over the ball, and there are two of them. One of them is much more famous than the other. The second one is sort of neglected, but it turns out to be important. The effect of when air goes past a spinning ball and remains laminar, which it actually doesn't, but you can sort of approximate it as laminar for at least a long part of its flow. That's called the Magnus Force, and we'll see how it's directed. Basically, the Magnus Force is a force exerted by the air on a ball, and oddly, it is not a drag force anymore. It's a lift force. It pushes the ball to the side, which it's our first lift force. It's not necessarily up. It can be in any direction. It depends on the spin of the ball. The other effect is called the wake deflection force that comes about because as the air goes past a spinning ball, the point at which it breaks away from the surface and becomes a turbulent wake is asymmetric between the top and the bottom of the ball. The wake then that forms it's offset. It's not right on the center line of the ball. It's cockeyed, and that produces a force on the ball that is also a lift force. All right, so I'll try to give you an idea of how these lift forces show up, and we can talk about how they affect sports, balls in sports. The Magnus Force, so this is the more famous of the two, appears even in laminar flow. So it's a direct result of streamlines going around the ball, the presence of the ball surface moving, and it needs viscosity a little bit to interact between the ball and the air. So we've still got a ball sitting here. We're with the ball. We're not spinning with it, but we're standing with it. And the air is going past it, heading to the right. So as usual, the air encounters the front surface of the ball, bends around it, and in the act of bending away from the surface, it's pushed away from the surface by high pressure. So the ball develops high pressure at its front. Same as always. But at this point, things stop being the same as always. The airflow that goes over the ball, and in this case, I got the ball spinning clockwise from your perspective. So the air going over the ball is moving with the ball surface, or the ball surface is moving with it. The air going under the ball has the surface moving against it. And the air is aware of this, the air in close, and it affects the whole flow. So the air that goes over the ball and has the ball moving with it goes especially fast near the surface. it not only especially fast, but it follows that surface for especially long. And when it leaves no longer on the center line of my story, but rather down here at the shifted downward. So those streamlines that we're following here make a especially long inward bend toward the surface. And for that to happen, for them to bend toward the surface and accelerate toward the surface, something's got to push them. And this something is the atmospheric pressure air far from the ball. It must be higher in pressure than the pressure right near the surface of the ball. So there's a net push towards the ball. So these streamlines are being bent inward by very low pressure right at the ball surface. And not only is it low pressure, but it extends for a long distance on the ball surface. All right? On the bottom of the ball, it's different. That bend toward the surface is kind of lame. It doesn't bend very far. These, incidentally, are actual calculations. This is real. This is really what the air does. Of course, calculations and real are not necessarily the same. But this is a pretty accurate representation of what the air does. It flows here, trying to go around the bottom. The bottom surface of the ball is heading towards the air. The air doesn't stay attached to it for very long. It bends and leaves relatively early in its trip around the ball. So that the airflow pattern that establishes itself in the ball looks like this is, you sort of have to take my word for it. Justifying the whole structure of it is complicated, and finally you have to get into the mathematics of how the flow works. But the result is not so hard to see. The result is you've got a lot of low pressure on one side of the ball and a lot of not so low or maybe even high pressure on the other side of the ball. The ball experiences a strong pressure imbalance. It's not like back in the day where the flow, I can flip back to this. Maybe it'll let me go back that. There. This is the unspinning ball. The flow is symmetric all the way around the ball. Every point is balanced by a point on the opposite side of the ball that is at the same pressure. That's gone in a spinning ball. One of these days I'll learn how to use the numbers to jump from one slide to the next. So you get a net push. The ball is pushed. It's pushed primarily at right angles to the airflow. So the airflow is coming along horizontally. And the push is primarily at right angles to horizontal, in this case, vertically upward. There's a little bit of a downwind push, a drag force that shows up as well. So I should say, to the extent that this force, represented by that arrow, is pushing exactly at right angles to the airflow, that's a lift force. Again, that it's upward. Well, in this case, it's upward, sure. But if I inverted the slide, it would still be correct, and then it would be a downward lift force. So it's simply that it's at right angles makes it a lift force. To the extent that this force is downstream in the direction in which the air is flowing, that's a drag force. So the point is this force is both lift and drag. The drag force part of it has the name I mentioned a couple times ago. It's called induced drag. It shows up whenever you try to get lift from the air. The act of deflecting the air involves doing work on that air and giving the air itself some energy. And that air, in taking away your energy, it takes away some of it. It has to suck that energy out of something, so it takes it out of the forward movement of the ball through the air. So anyway, you get both a lift force and a drag force. The effect is significant. This sideways. I should describe the other lift force first before showing you these. You okay with the fact that you get a force to the side in a spinning ball as air goes by? Or questions about it? Anything? All right. In reality, air doesn't follow streamlines all the way around the ball. It breaks away eventually. You get a turbulent wake behind a spinning ball, just like you get a turbulent wake behind a non-spinning ball. But the wake is shifted. It's not on center anymore. It heads off to one side. It's pretty easy to see why. Again, the bottom of the ball is heading toward the wind. So the wind's going by, the bottom of the ball is heading toward it. It's rubbing even worse than it would in a non-spinning ball. And so the airflow going under the ball runs into problems earlier and breaks away earlier than the air going over the top of the spinning ball, given this particular spin. That air is helped along its trip by the spinning surface. So the wake is asymmetric, and it creates another force on the ball. And that force is in the same direction as the Magnus Force. So you can't distinguish them just by which direction they act. You have to distinguish them by much more careful studies. And people have done these studies. And both of these effects are present, the Magnus Force and the wake deflection force. They're both present, and you can change the relationship between them by painstaking changes in the ball itself and in the airflow. But we'll just lump them together as the forces that push on a spinning ball as it goes through the air or the air goes by it. All right? The forces are real and pretty significant. I may be able to get them to happen for you with a beach ball. It's sort of iffy. If I spin this beach ball back towards me, so I'm giving it backspin. The names for spins are often associated with the top surface. So a backspin is when the surface comes back towards the thrower. You don't need to remember the names. They're conventions. And topspin is when, it's topspin. Backspin, topspin. The names are arbitrary. People made them up. Topspin is when the top surface is actually going in the direction of the ball. If I give this backspin, then as it's going like this through the air, it's the air over the top that follows the surface the most, the longest. And the air will leave heading somewhat downward. So can you picture that? The air over the top is coming back. It's coming backwards as the ball moves forward. That air arcs over and leaves down toward the floor. The consequence of pushing that air down toward the floor is the air pushes the ball up toward the ceiling. It gives an upward lift force. And when baseball is thrown normally, the back is pulled back towards the pitcher tends to pull back on the top surface and give it backspin. So it gets this upward lift force. It's typically not enough to make the ball actually arc upward for a baseball, but for a beach ball, I should be able to get it to arc upward. So I'll try it a couple times and we'll get it eventually. Can you see it? It was going up that time. At the very least, it's not falling properly. And that's true of a baseball thrown with a lot of back pull. The ball, as it heads to the right here, fails to fall properly. It hangs there extra long. The alternative is to throw the ball so it has very little spin and gets very little of this lift, which can be, a pitcher can throw that way, in which case the ball falls normally. And since having it fall normally is kind of exotic, it's described as a sinking ball. It's sinking only because it's falling. Let me try this one more time. Okay, that's actually pretty decent. This toy is meant to do the same thing. If I put this ball in here, it should give it a lot of that same backspin and make it arc upward. That one definitely did. That was my best one. Ooh, ooh, ooh. One more time. You can try this after class. Okay? So it's getting an upward push from the air as it deflects the air downward, either because of the Magnus Force or the wake deflection force, or both. You okay with that idea? Well, this is spin with it coming back at us. Actually, the sport in which that is most important is golf. You might not think of golf as involving curveballs. In golf, the ball is hit typically on the low side by the club, like it's chopped like that, and so it leaves, I should do it with a big ball. It's chopped down here, so it leaves the club with that same spin. And as a result, the golf ball, even though it's angled initially very low to the horizon, it's not, if you really want a non-spinning ball to travel as far as possible, you want to hit it something like 45 degrees. It's a little modified by air resistance, but not a huge amount. But a golf ball is hit much lower than 45 degrees, and yet it travels like crazy. It's actually flying. It's got so much backspin, and it depends on the club and the ball and all sorts of things, that it's getting a huge upward push from the passing air, and it fails to fall. It just heads along. And there are people who can hit the ball so that it not only does it go just hang there for a very long time, but it actually arcs upward. And apparently people can do loop-the-loops. You can actually make it go and go back over your head with enough of this lift force. All right? Other sports in which this is important. Well, this is soccer. The bend it like Beckham. Is this part of the cultural vocabulary anymore? Curving a soccer ball is the same thing. You give it a spin, and it will curve as it travels through the air, pushed by these lift forces. The direction of the lift forces depends on the direction of the spin. So if you give a ball top spin, so it's spinning the opposite of what I've been describing up until this point, it will deflect the air upward and get a downward push from the air, downward lift force, and that's apparently very important. Because I was a kid last time I played tennis. To get a tennis ball to go extremely fast over the net and still stay in, you need to curve it. So it clears the net and yet dives toward the court. And so that involves hitting it like this, so that you spin it this way and it dives downward by deflecting the air. And you can make it deflect to the sides. These are the famous curveballs in baseball. There are a bunch of different names. The only one I don't even know which one's the official curveball, alas. Different spin axes give you different directions of curve. Yeah, Dakota? It will be, is it considered a force on the ball or the air? It's both, of course, because of Newton's third law. So the ball deflects the air, which involves pushing the air to the side, and the air pushes back. So if you watch the air, if you could paint the air colors, you would see, oh, it's pushed off to the side by the spinning ball. Okay? Any other questions about the spinning balls and air? I mean, whatever your favorite sport is, it's likely to have these curveballs in it. Yeah? Does the pressure difference have anything to do with where the ball goes? Absolutely. It completely determines which direction the ball is pushed. So if you get the pressure difference in either, I'll go back to the Magnus Force because it's got the prettier drawing. But by spinning it this way, you get the low pressure on this side. And so the ball is going to accelerate towards the low pressure. But if you spin it the other way, the low pressure is going to be on this side, and it's going to accelerate towards that. So by picking the axis about which the ball is spinning and how fast it's spinning, you can determine which direction it will curve and how sharply it will curve. To get a curveball, to allow it to curve a lot, you need often to give it time to accelerate. So curveballs are, certainly in baseball, are thrown slower, deliberately slowed down somewhat relative to a fastball, because you need more time for them to accelerate and turn. So instead of throwing them at 100 miles an hour like the modern people do, it's more like, I think it's like 70. Okay? And you can do all this stuff. I mean, volleyball has these same things. The other thing to pay attention to is balls that don't spin, that aren't spinning. When they're not spinning, they don't get these forces exactly, but they do get a force related to these, which is as the air goes past imperfections in the surface or structure in the surface, as in the stitching on a baseball, that air in the innermost layer can get can begin to tumble. The boundary layer can tumble. And it can act like the dimples on a curveball in that one location. Dimples in a golf ball in that one little location. So the air begins to tumble there and shrinks the wake on one part of the ball. So for example, suppose we throw this ball and that little filling nipple there, the air that goes past that, the boundary layer trips, as though it went over a dimple in a golf ball. And it tumbles here, and the wake that forms behind this spot, along this stripe, shrinks in size, right? Without that structure, you get this great big huge uniform wake forming behind the ball. With that structure, you get a crack in that wake. There's a little part where the air follows the back of the ball longer and then breaks off late. That ruins the symmetry of the wake. And when that happens, there's going to be a force to the side. There's going to be a lift force. And so the ball will abruptly go towards, in this case it would be, you get a little bit of high pressure, it'll go away from that region. Don't quote me on this, I'm thinking on my feet, which is always dangerous. I'm having trouble already thinking at all. So the ball will dither to the side. So when a ball is thrown, if the ball is spinning to some extent, the location of that defect is going to average out pretty nicely. And so it'll have no important influences. But if the ball is thrown so that it's really not spinning, a knuckleball, then that defect becomes really important. The ball can actually curve away from the defect. And if the defect is just gently wandering around, the ball will curve, and then it will stop curving. Then curve, and then it'll stop. And it becomes really erratic and hard to deal with as the person receiving the ball. So a real knuckleball is thrown with very, very little spin. And the defects on the ball then cause it to dither around as the weight fluctuates in shape. Is that okay? And this is why, as balls get damaged, the umpires substitute them out because nicking the ball, putting those defects in there creates these structures that you can use to make asymmetric wakes and push the ball to the side or up and down, whatever. Any other thoughts or questions? All right. Okay, so that's I think, adequate justice to balls and air. All those sports deal with all these same issues, and that's life. Okay. So I'll leave balls and go on to airplanes. One value of bringing up the Magnus and wake deflection forces and the knuckleball forces is that they introduced this whole idea of lift forces. And planes just take that notion of lift finally to the extreme. They support themselves against the pull of gravity with lift forces, pure and simple. So a seemingly off-the-wall question to go into this. When you're riding in a jet aircraft, so you're sitting in the seat looking out the window, and you can see often, you can actually see the engines, the jet engines. And so the question is here, as you're moving along at 600 miles an hour in your jet plane, from your perspective, the plane's motionless, the air is rushing at you off from the distance at 600 miles an hour. The approach speed is 600 miles an hour. How fast is the air, from your perspective, going as it's really in that front entry area of the jet engine's that big mouth of the jet? Do you understand the question? Are you okay with the question? The question is that air entering faster than 600 miles an hour, slower than 600 miles an hour, or about 600 miles an hour? How many think it's going much faster than 600? How many think that it's going much slower than 600? How about 600 itself? Okay, it's all over the map. Just because I may not get to this before the end of the hour, we can walk through it. That air, the mouth actually sort of is a small mouth that gets a little wider on its entry. And also, it is, there are blades there but it's kind of a small passage. So the air, that's another, mainly it's getting wider. So the air flows in and then spreads out. That's a diffuser structure. Remember diffusers, the opposite of nozzles? What happens when air enters a diffuser or goes through a diffuser? It converts kinetic energy into pressure potential energy. So its kinetic energy goes down, pressure goes up. The answer to this, I'll just give it away, is slower. The air slows down on entry into a jet engine. It is in part because it's going through a diffuser, in part because it's sort of hitting a wall and compressing, which is a feature that is not possible with water, but that is possible with air. Water, you can't pack it more tightly than it started. Air, you can. So the air entering the diffuser at the front of the jet engine slows down in part because it's allowed to spread out, and in part because it's being deliberately blocked so that its pressure builds. And it does enter at considerably less than the speed of the engine, of the jet through the air itself. And that's crucial because it's very hard to work with air that's moving 600 miles an hour. The fact that they can slow it down makes a huge difference. The same thing is true, particularly true for supersonic aircraft, which have to breathe in air that approaches them at faster than the speed of sound even. They actually can slow it down to the point where in its passage through the engine itself, it's traveling well below the speed of sound, and much easier to work with as a result. All right, so some observations about airplanes, things to look at. They use the air to support themselves. So they push the air down, the air pushes them back up and holds them up. They need airspeed to stay aloft. They use the passage of air, the flow of air past them to obtain lift forces that support them. So if the air stops moving past them, they lose the lift forces. The exception to this, which is a topic I used to teach but have left in the past, helicopters. Helicopters still have the wings of an aircraft. They're often called blades instead. But instead of waiting for the air to move past them, they move through the air. But it's the same idea. They manage to have airflow across their wings and therefore develop lift forces. A few other things. They seem to follow their nose up and down, but it's more complicated than that. And they often have wings that change shape. If you've flown in commercial aircraft, you've probably noticed that during takeoff and landing, the wings get larger. They put surfaces out from the front and back of the wing that make it wider and more heavily curved to deal with the fact that they're traveling slower during landing and takeoff. And they propel themselves with various systems, propellers and jet engines, and we can look at those too. So here's my list of questions to go after in dealing with airplanes, the first of which is, how does the airplane support itself? And so that's where we'll start. I don't want to even do that. Okay, go back. So how does it support itself? It deflects the air downward. So as it pushes the air downward, it's the air passing the plane that it pushes downward, and the act of pushing it downward, which ultimately deflects that air, is the action-reaction. The air pushes up on the plane and supports it. Now, the whole mechanism for how this happens is kind of complicated, and certainly I find it interesting. Hopefully you'll find it interesting. This is a picture of the cross-section of a wing. So here's a plane, and if we took out a saw and cut off a chunk of wing, and we looked at what was left, that sliced surface, it would look like this, although tilted like that. Okay? So that's the cross-section of a wing. And first thing to notice about it is that it's carefully curved and much longer than it is wide. This is a streamlined surface, and I mentioned briefly the idea of streamlined. A streamlined surface is one that allows for laminar flow as much as possible, and therefore has streamlines around it. As opposed to what? As opposed to turbulent flow. And a surface that is that promotes turbulence is described as a blunt surface. So if I take my pad of paper here and I make it move through the air like this is a blunt surface. It's going to create a huge turbulent wake behind it. On the other hand, if I turn it like this, now it's somewhat streamlined. It's got a rough edge in the front, but that's the basic idea. So the two possibilities are streamlined and blunt, and streamlined favors laminar flow. Even at high speeds, it does its very best not to trigger turbulence or try to discourage turbulence, even though it's going fast and viscosity is having a tough time keeping the air orderly. Well, if you take a surface, a structure like this slice through the wing, so we're basically looking into the wing like this as it's moving towards you and watching the air flow around it. As the air flows around it, it does some things that we're used to seeing. The air flows, the first surface that it sort of collides with, it produces high pressure as it bends away from that surface. But in this case, that surface where it hits is the underbelly of the wing, early in the underbelly of the wing. That air comes in there, bends away. The streamlines below a certain sort of critical line bend downward, and the ones above it bend upward. And as they bend away from the surface, they're pushed away by high pressure. And there's high pressure here on the underbelly of the wing, accompanied by low airspeed. The air here has slowed down as indicated by the widely spaced streamlines. So this air is nice, slow-moving air. You could hang under the wing, and the breeze would be relatively slow. It'd still be 200 miles an hour maybe, but not 600 miles an hour. Okay, the air going under the wing bends away from it and leaves. And these streamlines, actually, if we follow them far enough to the left, now I've lost my, there it's back. If you follow far enough over here, way beyond the picture, they were coming in horizontally. They were trying to. So they're coming in horizontally. They arc up to meet the wing. And when they leave, they're no longer horizontal. If we follow these off forever, they never quite go back to horizontal. They head off, heading downward. The point is the airflow has been permanently bent. It's got a kink in it. From coming in horizontally to leaving, heading downward. So the airstream here has been bent away. It leaves the wing behind along the direction of the wing's tail. So it smoothly leaves the wing on the bottom. And this is high pressure all along the bottom of the wing because the air is consistently bending away from the wing throughout its trip under the wing, pushed away by high pressure at the wing. Okay? I'm here. Okay. The airflow over the wing does a very complicated maneuver. It bends first away from the wing, and then it bends toward the wing, arcs around really tightly, and continues along the top of the wing to leave in the same direction as the air under the wing. And as it bends around and over, it's bending toward that surface, just like on the sides of a ball. And that bend toward the surface is prompted by low pressure at the surface. So the atmospheric pressure can push the air toward it. So the air pressure on the top of the wing, particularly near the front, is very low, and that's the red color. The red end of the spectrum is low pressure. The violet end of the spectrum is high pressure. So you get low pressure, particularly on top of the wing and particularly near the front of the wing. And that then it smooths out towards the back of the wing, and then finally the airflow leaves. Well, the bottom line is, if you've got high pressure beneath the wing and low pressure above the wing, that's a big pressure imbalance, and it pushes the wing up and back, mostly up. To the extent that it's up, it's a lift force. To the extent that it's back, it's that induced drag I mentioned 20 minutes ago. And together they are the aerodynamic force on the wing. It's mostly upward, a little bit backward. And the fact that there's a force up on the wing from beneath it seems pretty straightforward. If if I blow air at the bottom of the surface, it's going to deflect off that thing just because it's kind of like a paddle. It's like hitting a pad of paper and deflected downward. What's bizarre is that the air going over the wing also creates an upward force on the, deflects the air downward and creates an upward force on the wing. But so I can demonstrate those two forces, those two halves to the overall force. This one seems pretty obvious. If I blow under the wing, I lift it up, right? No, I mean, a grade school kid would predict this would happen. What's a little more bizarre is if I blow across the top from the top, it goes up too. That's creating a low pressure on the top, that arc of the air trying to follow the surface. And why it follows the surface has got to do with viscosity and things. It tries not to leave holes behind the airflow. So it lifts it up. And those two forces together, so if you blow on, well, if I line it up right, I get both effects. The air going under the wing pushes up on it because the pressure's high. The air going over the wing pulls it up. Well, it doesn't really pull it up, but allows it to be lifted especially well by making low pressure over the wing. And those together then support the wing, or support the airplane. Questions about this? It's Friday, we're all just, anyway. So, this arrangement, this structure that shows up here depends on two things. It depends on the actual shape of the wing itself, how it's cut and oriented and all that, and also on how it is tilted, what's known as its angle of attack relative to horizontal. So that's this little note down here. If this wing were oriented exactly horizontally, it would have no lift force, not up, not down, because it's symmetric and there's nothing to prefer up versus down. It would do nothing. It was the fact that this wing was tipped upward that caused it to develop lift force. There are wings that are asymmetric, top and bottom aren't the same, and they naturally get lift force just even when they're approximately horizontal. Some wings are like that, some are not. This kind of symmetric wing, where if you sliced it right down the middle from front to back, the bottom is exactly the same as the top. You fold them over. That's especially good for something like an acrobatic plane. Planes can fly upside down, right? If you take this plane with that wing and you flip the plane upside down, so instead of flying like this, you fly like this, that wing will get the same lift as it did up. Works just the same. Real commercial jets, they're not symmetric exactly. So, is it Denzel Washington? It was in what was the name of the movie in which he flies the plane upside down for a while? Anyway, it works. It's not designed to be flown upside down, however. Acrobatic planes are. All right. The process of developing lift is an interesting one. This is a sequence of images of the airflow around a wing the moment after it was tilted up. It's a symmetric wing, so when it was horizontal, it was getting no lift. So imagine it was sitting there, it was moving through the air, or the air was moving past it, and abruptly the pilot arranged it so the wing tipped up. The moment after it tips, the airflow hasn't figured out how to flow around it yet, and it hasn't reached the real steady state that it wants to be in. This is the first arrangement. It tries, and it develops no lift. The flow is sort of has a symmetry to it. It's got this tight arc at the top front that's mimicked by a tight arc under the rear, the tail. But there's no overall pressure force on this wing yet. And the airstream arrives horizontally and ultimately leaves horizontally. But very soon, that funny structure at the back of the wing, where the air bends around the back of the wing to mimic the air flowing around the front of the wing, the air flowing under the tail here has a kink in it that isn't stable. It's too sharp a bend, too big an acceleration. So it blows away. So here it is blowing away, leaving what's called the trailing edge of the wing. It's still got that kink structure, that swirling. It's bending kind of counterclockwise as you view it. And here it is spinning counterclockwise. It leaves behind a little horizontal tornado that's spinning counterclockwise. And that's now out of view. And when that has left, the flow off the end of the wing is no longer kinked. And the structure, the flow structure is the one we just saw on the previous slide. So what's the point of this? The point of this is when you're rolling down the runway in a plane, initially the plane is essentially horizontal with approximately symmetric wings, oriented horizontally, there's no lift. And then when you're up to speed, so when the plane is moving fast enough, there's a moment when the pilot deliberately causes the plane to take off. It doesn't just sort of pick up for random reasons. The trick to getting the plane to take off, apart from going fast enough, is to deliberately tilt the plane. So you push the tail down by using lift forces with the air. You arrange it so the air is deflected up by the tail, and the tail goes down, the front of the plane goes up, and the wings tilt. The key point is the wings now have an angle of attack that's not flat. It's not zero angle. So the plane was going fast, and then tilt. And when the tilt occurs, initially there's no lift, initially being like for the first fraction of a second, and then that vortex comes off the back of the wing. And it's real vortex. That spinning tornado, if you get in it, you would notice it. It's really there. And on humid days, there are times when you actually can see the airflow because of humidity and condensation occurs in the air, and you can see the vortex come off. And when that does, suddenly the plane's got lift, and it begins to support its weight in the air. Okay? The vortex, the tornado that comes off leaves behind its presence at the tips of the wings. At the tip of the wing, even as the plane's flying along, it's been flying for quite a while, say, the pressure is high below the wing and low above the wing. That's the last drawing here. So if you've got high pressure on the bottom wing, low pressure on the top of the wing, air can flow from high pressure to low pressure by going around the outside of the wing. And it has a swirl to it too, like this. That's part actually of the same vortex that peeled off the back of the wing when it first took off. As that vortex comes off the back of the wing, swirling like this, where does it end? Does it abruptly stop right here? No, it actually attaches to the wingtips. And it follows the plane the whole trip. And only when the plane lands and gets rid of its lift does a reverse vortex form and finish it. It's basically generating a huge smoke ring. It's not worth going into all the details because we're almost at the end of the hour. But what I will leave you with is that swirl to the air, which was partly left behind at the beginning of the flight, will eventually be left behind at the end of the flight. The swirl around the wingtips is a significant thing. It follows behind any plane, and a second plane flying into those wingtip vortices will notice it. I've flown through them in various types of aircraft before, and they can turn a commercial jet flying into one of those vortices can actually go to about 45 degrees in 1 second. And then I was in a DC-10 encountering the wingtip vortices from a DC-10 ahead of us. And it took our plane, they hit it twice, and it took the plane to 45 degrees both times. Just, and if you hit them sideways, they're like going over a speed bump. So the wingtip vortices are real, worth staying out of. And you can see them during landing and takeoff in places with a lot of humidity, like Los Angeles Airport. There's a lot, you can see them pretty easily as the planes come in low over the streets. Anyway, we'll call it a day. And